Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math based of course, and as always it is an honor and a privilege to be serving you in a brand new school year here. We are in the fall of 2020, which we got to get out of 2020 really soon. I'm going to be doing some unit review stuff actually for one of my sets of classes, and I'll show you what the class is about and what the topics are and see if it works with you. I'm actually going to be doing two different videos today. One is more of a review, the one I'm doing right here, and the other one's a practice test. Now they're both similar kinds of questions that you're going to be getting, but during the review one I'm going to be doing a little more teaching during the problem, like explaining what all is going on, not just doing it. And then during the practice test, I'll just more so do the problems themselves. So if you feel like you got a good grasp of the material that I'm going to be covering, which I'll show you what it is right now, we're going to be looking at, as we look at some functions, we look at end behavior, domain and range, where intervals where something's increasing, decreasing, things like that. And then we're going to be looking at absolute value equations and absolute value inequalities, not only solving them, but also graphing them. So those are the unit things. This is part of an integrated mathematics 2 course, which covers a little bit of more intermediate kind of algebra 1 and geometry stuff with statistics thrown in. This is kind of algebra stuff that you're seeing right here. And we are in that first unit, and this is the review, of course. So like I said, this is the in the review video that I'm going to do, a little bit more slowing down and teaching with the problems that you see. If you feel like you got a good grasp of this stuff, just jump straight onto the practice test one if you'd like to see that as well. And I'm hoping, I'm saying this before I find out, but I'm hoping that in the description section below, first of all, I will provide timestamps for you for each problem, but I'm hoping I will also be able to provide you a link for a PDF of the problems that I'm doing right now. Now, in these problems, they're going to ask you to graph a couple times, and there aren't really graph axes on the PDF themselves. So if I do provide a PDF of that, I will also provide a PDF of graph paper for you to print out. Otherwise, just go ahead and watch along, and I'm glad you're here. Thanks for being here, guys. All right, so I'm just going to go ahead and start that off. Let's get started. All right, so with number one here, we have this graph, this absolute value function, and we are going to answer the following parts A through E. And I'll make sure to move my noggin out of the way when we get to part E. But part A, for this V-shaped graph, we are going to find the domain and range and use what's called interval notation here. Okay, so domain and range have to do with where are our X and Y values occurring on this graph in total. Domain is in reference to the x's, range is in reference to the y's. For domain, we're asking what x values does this graph actually hit? And I know there aren't arrows on this thing, but assume that this thing goes forever off the screen, forever up and to the right, forever up and to the left. Now, as I say that, that kind of answers the question, at least for domain here. It goes forever up and to the right. It goes forever up and to the left. It goes forever right and left here. This V shape never stops going right as it goes extremely high, and goes forever left as it goes extremely high as well. So the way that you want to say that here, this is an interval notation, but just speaking out loud, this would be all real numbers. We hit all of the x's on this graph everywhere left and right forever. Now, interval notation does this thing where it either uses square brackets or parentheses to indicate whether we are hitting a certain endpoint and how far left it goes, and whether we're hitting another certain endpoint and how far right it goes. If we have all real numbers on x, we are talking about going from negative infinity to positive infinity. We are going forever on these things. So I would put going from negative infinity, that's an 8. I want a sideways 8, negative infinity, to positive infinity, and infinity is not actually a number, neither is negative infinity. So the parentheses I'm going to put here, parentheses means we are not including those points that we're talking about. Infinity is not a number, so we never reach infinity. We never actually equal it. That's why we're talking about a bound which we do not approach and reach there. So that would be the answer. We can't really put all real numbers if they want interval notation. Range. Range is about the y values, and you can tell, although it seems like we go up forever, which we do not go down forever. In fact, it only goes as low as what looks like, if the scale is 1, 2, 3, 4, 5, looks like as low as y equals -1. This vertex, in fact, which might help me later anyway, is at -2, -1. And this is the lowest y value we ever get. That is actually the minimum value. So the range here, it goes as low as -1, and it goes as high as positive infinity, which of course we do not include the infinity. but we do include the -1. So I'm going to put a square bracket there. This is equivalent to me saying in inequality notation, y is greater than or equal to -1. Right? That's the equivalence there. If it just said y is greater than -1, I'd put a parenthesis, but this is a square bracket because we do include -1, and of course we do not include infinity. So you can tell, as I'm saying here, I just answered 2 small questions there, but I taught it through. So if I get a domain range question on my practice test like that, I'm going to say a lot less on those fronts. It's teaching it. I'm just going to kind of go to the answer, maybe say some stuff as I answer it, but I want to get ready to answer the next question after that. Okay, state end behavior, part B. Now, end behavior has to do with what does y do as x goes forever left and as x goes forever right. So what I'm first going to state here on both of these is as x approaches negative infinity, y approaches blank. And then we're going to say as x approaches positive infinity, y approaches blank as well. This is used a lot when you do higher order polynomials and absolute value functions as well. When you use squares and cubics and stuff like that, you'll be using this a lot as well. And there's a way to notice it, not just from the graph, but the equations. But from the graph here, we can see as x goes forever left, y looks like it's going forever up. End behavior means what is it tending to, or what is it trending toward as we go forever toward the infinity. Y never starts to fall down later over time, even though it does at this point. Then it goes back up. But as x goes forever left, y is going forever up toward positive infinity. It increases without bound. And as x goes forever to the right, y is also going forever up like this as well. So we don't know what's happening in between, or at least we don't describe it, though we know it hits that point there. Okay, next question is, what is the minimum? Now this goes back to that vertex thing right here. Minimum means the lowest value. Okay, the lowest value. And they are not just asking for the coordinate pair, really. Technically, they want the y value here. I can say, this is extra information, but I'll say the minimum of -1, now that's the answer, occurs at x equals -2. Here, I'll put y equals -1 so you know for sure here. That is the actual answer right there. The minimum is at y equals -1. I added some extra stuff and said where the minimum occurs for what x value, but the y value is that guy right there. And that's kind of what we're using. All right, part D, list any intervals where the function is increasing, give an answer as an inequality. Now, for this here, when we're talking about intervals of increasing, we're saying as x goes right, what is y doing? So x starts at the very leftmost infinity point, negative infinity point, and as it goes right all the way to the vertex here, it's going down, right? It's decreasing all the way up until x equals -2, and it starts increasing after x equals -2. And at x equals -2, it reached its minimum. It's neither increasing nor decreasing. It kind of just changes direction. So it's decreasing here, and it's increasing here. So to answer the question, where is it increasing, give as an inequality. That's any time after x equals -2. That means it's increasing at any point where x is greater than -2 there. Okay? That is the interval for which that occurs. Anything after x equals -2, your graph is going up, and it continues going up at that point. And last but not least, part E, and let me move my ugly mug here. Let's go that way. Write the function for the graph above. So let's erase some of the stuff that we now have here, get rid of all that, and let's write here what is drawn. Now, this function, this is an absolute value function. So we should do something with the general form for absolute value, which is vertex form here. It's going to look like this. Some f of x equals, or y equals, and you got some a value times some x minus h value plus k right there. A is going to represent the stretch factor of your graph, or in this case, really, because they're linear-ish, the slope. A is going to represent the slope of it, and I'll keep that one under wraps until we find h and k first, but that's the slope. And h and k are in reference to your vertex. Now, we already saw what the vertex was. you're going to have to be careful when it comes to the h value because this is x minus h, and whatever h is here, remember this was -2, -1, whatever h is, actually, we're going to be subtracting it, which means it becomes the opposite. So, to start this thing off here, h is -2, k is -1. So if I'm going to write out this answer here, it's going to say f of x equals, there's some a in front I haven't gotten yet, and we're going to do x minus h, x minus -2. We're going to do the opposite of -2, or of minus, that's plus. So x plus 2, and then we have the plus k, plus -1, that's -1. Okay, the k is already negative and we are subtracting. This was a -2 and we are adding. Notice the opposite, same. A is the slope of this thing, and it goes, because it's an upward facing V shape, it's going to have a positive A value. If this was an upside down V shape, it would actually have a negative A value. So let's look at what happens as we go up and to the right. Find a point that you know for sure that this thing's crossing through. Maybe you can tell it hits here. But if you can't, it for sure crosses right there at 0, 3. So it goes from here, it rises 1, 2, 3, 4, and it runs 1, 2 right there. A rise of 4 and run of 2, that slope 4 over 2 is also 2. 2 over 1, which is 2. So 2 is my A value right there, and that is an equation for that graph. That's in function notation with f of x, and there you have it. So that answers all of number 1 within here. We did some analysis of this graph, as well as getting an equation out. And I think that's the only one in the review that I have like that. We will be graphing, I believe, some things regarding absolute values. However, we're going to dive more into solving with inequalities and things like that as well. Okay, so now we're going to transform absolute value graphs here. So no more analysis of it. Just talk about how is f of x, this parent function, equals the absolute value of x, how does it transform into this g of x here in a, b, c, and d? So to kind of make sense of what's being asked here, and I'm going to draw this generally, and by the way, the next question after this, number 3, asks you to graph all 4 of these things. So we're going to graph all 4 of them afterwards. But to make sense of this for now, f of x, which I'll draw in blue, this is called a parent function. Now a parent function is a function of its type, this is an absolute value type, that is in its most basic form. There is no vertical or horizontal shift here of the vertex. There is no stretch other than just a slope of 1, and it's right side up. This graph kind of just looks like this right here. Just hits the origin and V's up. It goes as much up as it goes over. Up 1 over 1 like that. That's our parent function. I'll do basic drawings of these graphs because maybe it'll help you get the understanding of what I'm describing here. So for A, right here, I'll draw in green. This has a vertex. Remember, it's opposite. If this is the f of x equals a times x minus h plus k, x minus h in absolute value. If it's like this, notice how h and k is your vertex here. H, of course, is the opposite of what you see here because it's minus h, it's minus 2. That means h is 2, positive 2. So here your vertex is positive 2, and k plus 3, k is 3 right there. So we're going to start at 2, 3, and then there is no change in slope. It would be a 1, just like this one would be, so it would go up and over just as much as the blue one did over there, and of course over here. So how did f of x transform into g of x here? What did it do going from blue to green? That's what they're asking us to do. And essentially what we do, we keep the slope thing the same, and we go over 2 to the right and up 3 like that. And that becomes the transformation of this graph. And that's what you have to describe here. So that's what I'm going to do right here in green. I'm going to type this one out for you guys. This is more in mathematical terms here. I'm going to shift f of x 2 units horizontally to the right and 3 units vertically up. I don't know if I have to use vertically and horizontally if I'm saying right and up, but that's just giving you the idea of they are vertical and horizontal shifts, and that's what occurs. And that's all that happens here. Again, there's no sort of stretch or flip or anything like that. That's all that remains on that guy, and that's it. You don't have to draw these, but you do want to make sense of what's happening or pull out the information to really help you nail what it is that actually occurred there. All right, part B, a brand new g of x right here that I'm going to mark in purple. One second, I'm still on my text form. Let's go in purple here for B. All right, so g of x equals 2 times the absolute value of x minus 5. All right, so first of all, this 2 here is what we really got to adhere to now. Instead of being the 1 that you don't see here, this 2 means there is going to be a vertical stretch. A vertical stretch. Everything, we talked about this being slope, but a better way of also mentioning it is everything is 2 times taller than it was before. So this graph, if I don't shift it just yet, but just this graph is going to be 2 times taller than it was before here. And also the vertex, there is no minus h here. That means there is no horizontal shift, but there is a vertical shift downward 5 units. So it's going to be looking about like that right there. So twice as tall as blue and now shifted down 5 units. And let's describe both of those together right here. Let's vertically stretch this graph by a factor of 2. What that means is I'm making every height twice as tall as it previously was. Instead of going up 1 over 1, now I'm going up 2 over 1 each time. And also, this time I won't say vertically here, but just shift, let's just say 5 units down. I think that kind of stuff can kind of be okay when it comes to these descriptions. You don't have to get very wordy. Just use enough that kind of looks like it does make sense there, and that's that one. All right, part C, g of x equals negative absolute value of x minus 3. Let's see what color I can use here, kind of this dark red. So in this kind of dark red right here, this time we see our first negative. We see our first negative, and this is in reference to the slope. There is no number in front, so we're assuming, it's a 1, but it's a negative 1. So instead of going up 1 over 1, we are going down 1 over 1. We are taking what was the blue graph before like this. I'm going to draw right over it. These aren't going to be perfect. Remember, I'm going to draw these later, right? So these aren't going to be perfect. So like the blue graph right there, only now it's going to be flipped upside down. We are going to reflect this like this, and really it's called reflecting over the x-axis. Here's the x-axis, and it flipped over. See blue? Blue flipped into that red right there, like right there. There's that flip. So I flipped it, and there's going to be the plus 3 we'll talk about here. This is part of your vertex. Remember, it's opposite of minus h. We're subtracting a negative 3, really. So we are actually shifting this thing left 3 units, and there is no plus k that you can see, so we're adding 0. That means there is no vertical shift. Your vertex is at negative 3, 0. So I'm going to shift this guy 3 units here to the left. Let's go ahead and take a peek at that. It's going to maybe look something like that there. And let's go ahead and describe that in good detail. And then my picture is going to cover this problem afterwards, so I can do part D and you can see it. But let's go ahead and say reflect f of x over x-axis, over the x-axis. You could probably say flip it upside down, but you want to reflect this thing first, because if I did a vertical shift and then I flipped over, then I'm actually going lower than my position I wanted. So reflect it first, and then shift 3 units to the left. Let's just go ahead and say that for now. That looks good. Okay. Take a look at that for a moment, or pause this screen, because pretty soon I'm going to move my picture right over there so you can then see everything in part D that we do. All right, here we go. Here I go. Bye-bye. All right, part D, last one here, and let's get another color. Oh, how about orange? Kind of an orange. There we go. All right, last one. G of x equals 1/2, a fraction, times the absolute value of x plus 1 minus 4. So we're going to be doing a lot of changes here. This is, 1 that was, this slope right here. That's up 1 over 1. This one of 1/2, it's not going to be too hard. That's up 1 over 2, right? So we'd go from here, we'd rise 1. Let's see. From here, we'd rise 1 and run 2, kind of like that. So it's going to be a little wider. People kind of describe it as being wider there. So instead of blue looking like it is, our orange graph is going to kind of do that. That's probably too wide, but that's okay. I just want to exaggerate and show you what it's doing. It's half as small, half as short as for every y value. every y value is half the height at every x value compared to blue right there. Your vertex, remember opposite, we're at -1, and then same, we're at -4 right there. So we got to go left 1, 4 down right there, and that would be the equivalent of the orange. Again, I'm going to graph all these ones in full for you after this. Just keep that in mind. So let's go ahead and describe this guy right here. I'm going to start with the stretch factor change. And remember, you don't just want to say it's wider. You could say it has a slope of 1/2 now. I didn't flip it over, but I will say vertically shrink by a factor of 1/2. So this time everything is half the height as it was before at every x value. And also then shift 1 unit to the left and 4 units downward. Okay, let's kind of just be smallly descriptive like that. I think that's going to be okay for us. If that's okay with you, it's okay with me. So those are the descriptions. That's thorough. That's thorough. That covers it. So there we go. All right, moving me back because we are going to go ahead and move on. If there are no questions, how could I take questions anyway? Let's go forward. All right, graph the functions. I think I'll probably make myself smaller there if need be. All right, there we go. Graph the functions here. G of x. This part A is going to be the part A that was over here. See, that's even in the same spot. G of x equals absolute value of x minus 2 plus 3. We kind of just did it before. Let's pull out the information again. The vertex is at 2, 3. Again, opposite same. And then your slope of your thing, it's really the a value, but your slope, your m, is up 1/1, like that. So we're going to start at 2, 3 like this, boom. And we're going to rise 1, run 1 to the right. And then we're also going to rise 1, run 1 to the left, because this is a V shape, and that's where your vertex appears there. So I kind of ran out of room on my graph there. I'm going to go ahead and draw this purple line through those points, starting from the vertex with an arrow, and that will be my graph. I get to kind of go faster on some of these as need be, and I think that one fit just fine. All right, part B, g of x equals 2 times the absolute value of x minus 5. Again, this, if you want to write it in its like proper vertex form, you would put x minus 0 right there to just make sense that that vertex, once again, is 0, comma, -5, and there's no -0 in case you put plus 0. Your slope here this time is 2, or 2/1. If that helps you, pull the information out. So I'm going to start at 0, -5, and then I'm going to rise 2 and run 1. Looks like my picture does not interfere with this, which is good. Rise 2, run 1, and I'll go as full as I can up and through the graph there, and then to the left side. Again, as they V-shape, this would only flip upside down if your a value, or your slope here, was negative. And then you'd be looking at an upside down version of what we have there. All right, so let's go through there. That green is a little darker. That's my bad. But that is my graph. You can use a ruler on those. And like I said, hopefully the graph paper I provided you is kind of good enough if you printed this out. It's not going to look the same as these ones, and you'll have to scale on your own. But they are grid-lined and even scaling on those. All right, that's A and B. Let's go ahead and do C and D. And again, I kind of already did these, but now we're doing them on proper graphs. You get to see them again. Part C, we have kind of a plus 0 right here. And remember, we're going to go opposite of plus 3 because it's subtracting a -3. And then 0 means we just shift to the left 3 units like you saw before. And the slope here, even though you can't see the number, you can see the sign is negative. Not seeing the number means it's a slope of 1. In this case, a -1/1. So now we go down 1, right 1, etc. through this graph. On the right side of the vertex and the left side of the vertex, we also go down 1/1, but of course we're going left. So there you have it. We got, hold on, trying to get blue going. And there we go. On that guy and that guy. And we'll see if I have to move myself again for this next one. Last one here, part D. I know I had orange last time, so let's use orange again right here. 1/2 times absolute value of x plus 1 minus 4, and we're going to go ahead and shift this guy here. The vertex is at -1, -4, again, opposite of +1, and same on that one. If you want to know why that is, I'd have to save that kind of for a different talk, something that might help you over time as we go through. And this slope is 1/2. Slope is 1/2, and that doesn't mean I have to go up 1/2/1. I can go up 1 over 2. That's the reason I was plotting these other, or writing these other ones as fractions, so you understand that rise and run. So I'm going up 1, right 2. It looks like I will get in the way here. Not really. I'll stick with me there. And up 1, right 2 there. You can see that point. There we are. And up 1, right 2 one more time. And then we go to the left, up 1, left 2. Okay. So when I do the practice test version of this thing, maybe I will not be... I'll say the information we're pulling out, but maybe I don't write it. Just for, efficiency. Make sure that we can cover that a little bit faster, because this is the part where you're really being taught it as if you didn't really feel it out that first time. But that's how we graph those things, by shorthand without a table. That's how the vertex form works. All right, let's go ahead and move on here, and let's go ahead and solve these guys here algebraically. You can get a little bigger again. Solving these algebraically and solving an absolute value function, the first thing that you want to do here, and this is going to be true for both of these sets, is we want to isolate the absolute value quantity here. I want to get this thing by itself on one side of the equation. To solve for x, to get x by itself, we have to first get the absolute value by itself, because we're going to do something after we do isolate that absolute value. So I'm going to start, 2 is multiplying with this. I'm not going to distribute. Absolute value is a very protective form of parentheses, and it does other things, so you want to make sure nothing enters. Keep the 2 out. 7 is being added in the end. Let's go ahead and subtract 7 to start with, therefore, to start to get the the absolute value quantity by itself here. And now we have 2 times the absolute value of x minus 3 on the left, and on the right we have 15 minus 7, which is 8. Okay. Now I'm going to go ahead and divide both sides by 2 to then get the quantity completely by itself on the left side, and now we're going to get absolute value of x minus 3 equals 4. Okay. In teaching this, because that's what I want to do here, think about what absolute values do, and think about what this said. Forget the fact that it says x minus 3 in there for a moment. Just think that you're taking the absolute value of something. My question to you is, what can you take the absolute value of to get 4? The absolute value of what gives you 4? 4 is one of those numbers. The absolute value of 4 is 4. But you can also take the absolute value of negative 4. And the absolute value of negative 4 still gives you a positive 4. So consider the idea and understanding that this x minus 3 represents some number. The x minus 3, the thing that you're taking the absolute value of, can be either one of two things. It could either be a positive 4, or it can also potentially be a negative 4, because either way, when you take the absolute value of that, you get 4. So now we want to figure out then what values of x that we subtract 3 from give us 4 or negative 4, right? So we're going to add 3 to both sides to figure that thing out. So plus 3, let's just start with this one on the left here. We're going to get x equals 7, because 7 minus 4 is 4. Okay. Or what happens on this side? We can add 3 to both sides here. Negative 4 plus 3 isn't negative 7. It goes the other way towards 0 as we add, and that becomes negative 1. X equals negative 1, because negative 1 minus 3 is negative 4. Take the absolute value of that, you get a positive 4. You can double check that stuff, but you get 2 solutions here. You often do. When we start doing things with inequalities, you might see some cases where some special things come into play. I don't know if that happens here or on the practice test at all. Sometimes with an equal sign, it's possible to get no solution or just one solution. This one actually looks kind of like one of those special cases. Let's take a look at it. Part B, the absolute value of 2x plus 3, close that up, plus 4 equals 4. So do something in here, take the absolute value of it, then add 4, and you get 4. Well, what was it before we add 4? Let's check it out. Let's subtract 4 from both sides to figure out what just the isolated quantity becomes. The absolute value of 2x plus 3 becomes 0. Okay, 0 is a value without sign. It is the threshold, the barrier, the wall, the thing that divides what is positive from what is negative. 0 is neither positive nor negative, and 0 cannot obtain a positive nor negative sign. When you take the absolute value of 0, you get 0 out. All right, so there's only one thing you can take the absolute value of to get 0, and that is 0. So what I'm saying here is, we ask, what do we take the absolute value of to get 0? As I said, the answer is 0. So we kind of just drop the absolute value here. There is no either or case. There's no swapping of signs here. 2x plus 3 is going to have to be 0 for this to work out. All right, so let's subtract 3 from both sides. and we're going to go ahead and get 2x. Now, that's not what x's answer is, right? We still have to solve for x. 2x equals negative 3, and then we're kind of running out of space there. And then as we divide both sides by 2, we're going to end up getting a fraction answer. So we divide both sides by 2 there, and we get x equals negative 3 halves. As a mixed number, that's negative 1.5. As a decimal, that is negative 1.5. This is a fine answer there. It is correct. It is proper. It is the only one. You can double check it, and it will work out. So that's solving those algebraically. We're finding out what makes the left side equal the right, and we got it in both of those. Okay. All right, number 5, we are now going to solve inequalities algebraically, and we are going to graph the solutions on a number line. So solving inequalities is just like solving equations, only you have to deal with the greater than, less than. Just keep it there. Sometimes you flip it, and some things change here, and then the number line's there. But you still try and get this thing by itself by doing the same thing on both sides of the equation, and that's how I'm going to begin this problem here. So with this first problem here, the absolute value of x plus 4, close that, plus 5 is greater than 7. I'm going to subtract 5 from both sides like this, and then I'm just going to have the absolute value of x plus 4 on the left, and then we're going to have 2 on the right, because that's 7 minus 5. Okay, absolute value. Remember what happens when you take the absolute value of something. It essentially becomes its positive self. So if I take the absolute value of 10, that's 10. If I take the absolute value of negative 10, though, that's also 10. So think about this. We got to take the absolute value of something that is greater than 2. Negative 10 is a nice number that can go in here to make this work, because if I take the absolute value of negative 10, I get positive 10. Positive 10 is greater than 2. So notice negative big numbers are going to actually work in here, and positive big numbers. Not big, but numbers that are larger than 2. We have to stay outside of 2 units of 0. We have to stay more further away than 2 units of 0 on either side of 0, either positive or negative. That's where we start to write this split here. We say that x plus 4 would either have to be greater than 2, right, on the right side of 2, or x plus 4, that inside guy, would have to be less than negative 2, because we want larger negative numbers over here, because when we take the absolute value of it, then it becomes larger than 2. So notice if you have a absolute value greater than some positive number here, we're going to change the signs to negative 2, and then this greater than is going to flip to a less than on the other side. And I got to use this or thing, because this is going to split to the left and right here. We're going to have 2 different conditions, and we can double check some of these, but I told you about negative and positive 10. All right, now I got to actually solve for x, not just the inequality portion. So I'm going to subtract 4 from all these guys, really, if you think about it. Subtract 4, subtract 4. And ultimately, we're going to be getting, I kind of run out of room there, but we're going to be getting x is greater than negative 2, or x is less than negative 6. Okay, that's your final solution set right there. And I'm going to go ahead and graph this guy. And maybe we can talk about double checking what happens there, so we can then, make sure that that makes sense to you what we did. Now, graphing inequalities here, because it's exclusively greater than or less than, there's no equal to, we are going to be plotting an open circle on either boundary point. So negative 2, we'll get an open circle right here. And when x is greater than it, we're going to go ahead and graph that to the right. Greater than is to the right. Draw an arrow at some point. You say it goes on forever this way. Any of these points to the right of negative 2 are going to be solutions. That means any of these points I can plug into the original value, and it will work. X is less than negative 6 over here. Open circle on negative 6 to say negative 6 is not included, because it does not also equal to right there. And we draw an arrow to the left, and that is where x also fits. So it's weird to think about the fact, and remember what we're saying here. We found values of x that when we plug it into the original inequality right here, we would get a true statement that the left side would become greater than the right side. And this is the only problem I'm going to stress the importance of, where we say, how can small negative numbers, how can numbers that become more negative still help me get something that's greater than, when the lesser negatives don't really do that? And the answer, again, has to do with the absolute value. Let's take negative 10 as an example, which should be a solution to this. Negative 10 goes inside the absolute value with plus 4, and plus 5 is greater than 7. Negative 10 plus 4 is negative 6, but the absolute value of negative 6 is positive 6. See, we take these large negative numbers and they become large, I quote large because 6 isn't very large, but they become large positive numbers as a result, which means it does allow us to get greater than 7 as a result of that. That's what makes it a solution. If these numbers that are negative here, these numbers here are not large enough to offset the idea that when we add 4 to it, and then take the absolute value, adding 5 to it does not make it larger than 7. So these negative 6 to negative 2 do not work, including negative 6 to negative 2, and anything outside of them do. Okay. Again, that's my teaching version of this problem. I will go faster on these, and on the practice test, I'll go faster on them as well. Less of an explanation. This word or was important because of the split. You can't be 0 and negative 9 at the same time. You could be 0 or negative 9 at any one time. That's why that or is kind of there. This one actually will not inherit an or, and you'll see why in a moment. So let's go ahead and solve this guy here. Part B, 3 times the absolute value of x minus 5, and then minus 7 is less than or equal to 5. Just like the equal sign ones, let's go ahead and add, not 5, let's go ahead and add 7 to both sides here to start to isolate the absolute value. Not quite isolated just yet. We got 3 still there. Okay, and we got 5 plus 7, which is 12. Okay, now we divide both sides by 3 to get the absolute value quantity by itself. Not much different from what we've already seen before. And the absolute value, whoops, not red. The absolute value of x minus 5 is now less than or equal to 4. Okay. Now, unlike last time where it said greater, the absolute value is greater than something, where we had to stay more than 2 units away from 0, now this says less than or equal to. Now we have to stay within a certain amount of 0, right? You're within this radar, within this bubble right here. We got to stay less than 4 or equal to. So now, when we do this thing here, we're going to have 2 different conditions, just like the last time. The positive side has to be less than or equal to 4. And we're going to say and on this one, you'll see why in a moment. And this side has to be greater than or equal to its negative counterpart. Remember, greater than a negative means to the right? It means closer to 0. So we're staying within 4 and negative 4. This isn't our graph, by the way, because we got to graph what x is, not what x minus 5 is. I'm just giving you this within. That's why we say and. We got to be within this and that. Not within this or that, because otherwise you're kind of hitting every number in the book. We're staying within numbers, so it's going to be an and case right here. So let's go ahead and add 5 to all these right here, and we're going to go ahead and get our solution set, if you will. As the 5's cancel, we are then left with, on this leftmost inequality, we have x is less than or equal to 9, and here we have x is greater than or equal to 1. Negative 4 plus 5 is 1. So that's your final solution set there. If you'd like to create an and statement as this already is a compound inequality, but if you'd like it as a single inequality statement where these symbols all fall on the same line together, we can write it like this. Use the leftmost term here, 1, or the leastmost term, and say 1 is less than or equal to x, which is true. X is greater than 1, so 1 is less than x. And that x is also less than or equal to 9. So it kind of looks like that. A compound inequality with the inequality statements all together there. Boom. X is between 1 and 9, including 1 and 9. That's kind of how you can say it as well. And this one's kind of nicer because it allows you to better visualize what your number line is going to be. X is between 1 and 9. All right, so X is between 1 and 9. 1 is going to get a closed circle on it, as is 9, because they are included. That's what the or equal to means. And X is any number in between it. Now, if you don't use this compound inequality format right here, you are going to have to use the word and to indicate that it's not just greater than or equal to 1 or less than or equal to 9. What's a number that's greater than 1 or less than 9? Well, that's any number in history. 1 million. 1 million is not less than 9, but it is more than 1. So when you say or, you just need to satisfy one of them. We need the and there. We need the and there. Same reason why we needed the or here. You can't be 2 numbers at once on opposite ends of a spectrum. And the and here is because you need to stay within this set here. We can't branch outside of it. Okay. So that's our solution set right there with the closed circles. And there we go. And last one, part C. And then there's one more problem here with the graphing and number line part. Part C here, let's see what colors I've used. Okay, I'll use a green right here. Let's subtract 5 from both sides. Same idea, guys. This kind of stuff hasn't changed, but possibly a different kind of condition. In fact, I'm smelling a very peculiar specific case here where something kind of changes. 1 minus 5 is -4. That's what I did when I subtracted 5 from both sides. Now we divide both sides by 4 to get, again, the absolute value quantity by itself. And then we get the absolute value of x plus 1 is less than -1. Okay. Now we take this part and we state, okay, how do we create our inequalities to go and graph and do things? Well, let's be careful here because I want you to think about what's happening. On the left side, you have an absolute value. Doesn't matter if it's x plus 1 or x or whatever it is. In fact, just let's hide this for a second. Let's pretend it's just an x. The absolute value of some number is less than -1. Heck, let's even say equals -1 here. Can I take the absolute value of something and make it negative? That's really the question right now. Can I take the absolute value of something and make it negative? The answer is no. We can't. When you take the absolute value of a negative number, it becomes positive. When you take the absolute value of a positive number, it becomes positive. When you take the absolute value of 0, it becomes 0. Under no circumstance can you take the absolute value of something and make it negative. The only exception would be if there was a negative on the outside, but that's why we isolate the absolute value to begin with. So there is nothing on the outside that's affecting it. That's why we divide by this 4. That's why we subtract this 5 over. Which, by the way, notice it started as a positive over here. Subtracting the 5 is what made it negative, and that's what we have to adhere to. That's the point. So why did I put equals and just an x here? Because the point is whatever we take the absolute value of inside here will not only not be negative, but then it also can't be less than a negative, which is further negative. What numbers can we take the absolute value of that are less than -1? Nothing. That means what can we put in for x to make this a true statement? Nothing. This is what is called a no solution case. And I'm not sure how I turned from green to purple here, so I'm going to probably make these green again. So no solution here. There is no possible way that I can get a value for x that would make this thing true. Now again, as this is the teaching video, if you get something like this on the practice test, I'll be a lot faster in my talk. I'll just kind of explain why and then move on. Consider the alternative for a moment, just so I can teach it to you. What if instead this said greater than -1? What if it said greater than -1? Okay. We take the absolute value of something, and it's either going to be positive or 0. Numbers that are positive or 0 are always greater than negative numbers. Remember, this is a negative number here. This would always be a true statement. No matter what I plug in for x, I will always make a true statement. That means if it was greater than, you'd be looking at something that's all real numbers. You can plug in anything for x and you'll be good. So greater than and less than really change things with absolute values on here as far as solutions go, especially when you have a negative here, or even sometimes when you have 0. And there are rules included in that stuff that you'd understand. Now, how do we graph this? The graph is the solutions of the x values. All the points that we plot here are all the things that x can be. X can't be anything here. This is an empty solution set. There is nothing to graph on the number line. No points. You leave it blank. That's it, and that's all. If it was all real numbers, you would just go forever to the left and to the right with big arrows there to just say you can be anything. But this was no solution, and that would be it there. All right, I got one more problem set-ish thing here to do, and like I said, this is the longer video. Practice test video will, of course, be shorter, I assume. I think there are more problems, but less teaching. Solve first by graphing. We're talking about this guy right here. Solve first by graphing, and then solve algebraically. Use graph paper for the graphing. Show solutions on a number line below. So if I can get a PDF uploaded down in the description section below, you should see a thing in graph paper you can print out, or you have your own, of course. I have my own set of axes right here that I'm going to graph with. Okay, and then we're going to show solutions. Now, how do you graph something on an XY axis without any y's involved in this inequality here? Well, you got to create the y values. And how do you create them? You take the left and right expressions and you treat them as their own separate equations. I'm going to take the expression 2 times the absolute value of x minus 3 minus 1, and I'm going to say that this is one of my y values. I'm going to use this as f of x. My other y value is going to be this guy, just 3. Just 3. That's going to be my g of x right there. So if it helps, I'm going to go ahead and write 2 equations. F of x equals 2 times the absolute value of x minus 3, close that, and minus 1. And I'm going to create another equation that says g of x equals 3. And I'm going to graph these two. Now, before I do, You might be asking, where does the greater than work here? Should I say greater than and greater than? No, right now what we're going to do is we're going to graph these as if they are just lines. Okay, we're going to graph these lines here to begin with. And then we're going to compare f of x to g of x. We're going to figure out when is f of x greater than g of x. And we'll talk about that when we get to it. But first, let's graph these. This is your vertex form graph. We've seen a couple of these. I think I can do this pretty fast without pulling out the information and writing it. Let's just graph it. Opposite, same. Opposite of negative 3 is positive 3, so 3 to the right. Same with negative 1. Let's go down 1. That is the vertex of this blue graph right here. 2 is my slope, up 2 over 1, and because it's positive, we will go upwards on this V shape. We'll go upwards in both directions of the vertex, so, excuse me, over here as well. And let's go ahead and draw the lines of destiny. The absolute value graph is going to go up like that, boom, and up like that. That is my f of x graph. That's good. G of x equals 3. Remember, this means y equals. So it's y equals 3. Y equals 3 is be careful, it's not a vertical line, it's a horizontal line. We go up 3 on y, and it's all of the y equals 3 values all across here. So it's a straight horizontal line across y equals 3. And I'm going to go ahead and graph that one right there. Okay. So we have our two graphs in place. Okay. Now, we're going to solve this thing. We got to find out what values of x can I plug in here to make the left side greater than the right side. We will solve it algebraically next, just like we did the last problems to figure that out, but you can also do this on a graph. And you do this on a graph by comparing the y's of both of these graphs here. Why do we compare y's? Because this is an expression to represent your y value. If I plug in a number for x, I compute something, that's the y value for that x. That's why we say f of x equals blah, blah, blah. So this represents my y of blue. This represents my y of green. We got to figure out when blue y is larger than green y, which means we got to figure out when blue is higher up than green. We got to find out what values of x have blue points that are higher up than green. Okay, that's what we're doing. And I'm going to kind of scan this thing. I'm going to start from the middle and see if you can make sense from the middle and move onward from there. Okay, by middle I mean vertex. All right, at the vertex, at x equals 3, you can tell that the blue point is lower than the green point. Clearly, x equals 3 is not a solution to this, because when I plug in 3 here, blue will not be greater than green. It's lower than, you can tell. When I move further to the right at x equals 4, you can tell blue is still below green, and at 5, blue is equal to green. They actually equal in height right here, but it's not greater than, but it's a nice boundary point to make sense of the fact that, hey, we might be crossing right here. Let's go to the left and see the same thing. Notice that they're equal here. If we were to solve this by graphing and it wasn't equal to, these would be our two answers, x equals 5 and x equals 1. If we were solving, we would find the points of intersection. But we're finding out where these two things, where blue is above green, all right? So where is blue above green? Well, let's go a little further to the right, and you can tell at all these x values here, as blue continues up forever in this direction, as x goes toward infinity, y goes toward infinity, blue is taller than green at every value of x that is greater than 5. Look at all these, let's do this here. Give me one moment while I kind of tool this thing up. I'm going to kind of create like this shaded region of purple here that indicates all this stuff that's off the graph that you can't see, but all this region here that's greater than 5 is when blue is above green. Not at 5, but greater than 5. And that's one of my solution sets there. Remember, x is greater than 5 is an infinite number of solutions. 6, 7, 8, 9, 10, 1,000, 5.5, all those. X is greater than 5 is one of your sets there, because blue is above green. Blue is also above green when you go in this direction as well. You can tell. Look at all that shaded stuff. Blue's above green. Anything less than 1. At 0, at -1, at -2, and it goes up forever like that. Blue is above green. You don't have to do all the shaded stuff. I'm trying to give you a visual. Some people might not understand the visual. So x can also be less than 1, and apparently you'll get true statements there. So there's a nice or in between because it's that split that we talked about before. And that helps me solve that guy by graphing. So that's what I did. I graphed the two lines and I asked for what values of x are blue above green. You might not have the colors, but the V-shaped graph above the flat graph. right? It's all these points right here. Above green, above green, above green, greater than 5, above green, above green, above green, less than 1. All right. Solve algebraically, we just did some things like that, so I'm going to go ahead and rewrite this thing. This is specifically for confirmation purposes. As I've already taught it to you before, let's go ahead and confirm that we'll get that same answer, and I believe we will. So let's add 1 to both sides here, unless I made a dire mistake that I have not yet caught. I think all should be just fine. 2 times the absolute value of x minus 3 is greater than 4. 3 plus 1 is 4. Let's move me over anyway, because I know that we have to graph on this number line down here, ultimately. There we go. So this is where we create, this is where we divide both sides by 2 now. And then we have isolated our absolute value expression in this inequality, okay? And now this is where we create 2 different conditions, as we have to be greater than 2, absolute value has to be greater than 2. Either the inside guy has to actually be greater than 2, or it would have to be less than negative 2. For the same reasons I mentioned before, we have to stay outside of 2 units from 0 in either the positive or negative direction. I'm kind of running out of room, and I'm kind of running out of time here. As I add 3 to both sides, I'm going to get x is greater than 5 here, or as I add 3 here, negative 2 plus 3 is positive 1, x is less than 1. So there we go, x is greater than 5 or x is less than 1. It seems to match what I wrote right here, and it should be. That's going to be the same thing. Whether you solved it algebraically or graphically, literally, look, the graph, if we condense this graph, if we squish the y-axes and make it into a one-dimensional number line left and right, you're going to see the equivalent of it right here. It's going to start at 1 and then go to the left, and start at 5 and go to the right. We don't include 1 and 5, so we're going to do open circles there. So open circle on 5 and to the right that way are x solutions, and open circle to the left, or on 1 and to the left that way, arrow there, and those are my other x solutions. Okay, so again, when we substitute it, we're kind of comparing the y values if you see it on a graph, all that mumbo jumbo. All right, so that is it for this stuff, guys. That is for my review stuff. There was a lot more teaching. You can tell it's 50 minutes worth of those questions there. This other one should probably be half the time. I can't guarantee it. It'll probably be half the time. Keep that in mind. I will caution you prior to doing that practice test stuff with the idea that I won't be teaching as much as I will kind of be doing. And if you want to hear more of the teaching, of course, you would have been watching this video. So thanks for watching this video. I hope you did appreciate, I hope you appreciate the fact that you might have learned something here and there as you go along. You can tell I don't edit these things down. And stay tuned for kind of a part 2 with the practice test, guys. Have a good day. Take care.